We saw the simple problem of line fitting where we have a set of points and we want to find the equation of a line that minimize the sum of squares error. Let us look at this problem a little bit more carefully. So if you notice, objective function was something like 1 by n I is equal to 1 to n yi minus w transpose xi whole square. What is the error here? The error in this case is, if this is x and this is y, error is axis aligned. Or if you zoom a little bit, this is the error that we talked about. We did not talk about this error, the orthogonal distance. Indeed, as far as problem is concerned, problem of regression is concerned, this is a right error to optimize. But if you want to look at just as a line fitting problem, there are more different ways of looking at the error. One of them is orthogonal, a line that minimizes the orthogonal distance. Let us look at this problem. So we have a set of samples and we want to find the equation of a line that minimizes the orthogonal distance from the point. Something like this, where the distances are all orthogonal. So we know that given a set of points, mean is the point that has the smallest sum of squared errors or the distances. Indeed, mean is on this point, on this line. What we want to know is how we define this line. To formulate this problem, let us first subtract the mean from all the samples so that we get a new picture with mean as the origin, and let us look at one sample to start with. So this is our mean, which is the origin. Now we have a sample xi. We have a line defined by w. What we want is to minimize this distance, sum of these square distances. This is nothing but minimize xi transpose xi, this distance, square of this distance, the hypotenuse, minus sum of this distance square. Minimized over w. And this term is independent of the w. This problem becomes now, indeed we need to sum it over I is equal to 1 to n. So this problem now gets converted to maximization of w, the second term, that is I is equal to 1 to n w transpose xi whole square. This is nothing but maximization of W transpose xi. You can also look at this as So W transpose xi whole square. So this term that we are talking about, okay, maybe I should write this as in the matrix form. That makes the life easy. See, if you, this is nothing but W transpose X transpose X W. What is X here? So W is a D by 1 vector and the transpose is 1 by D. This is D by N, N by D and D by 1. So X is a N by D matrix with all the samples x1 to xn written in this form. And we know that maximization of this form, this quadratic form with no constraint on W is not going to give us any useful solution. So we would like to have a constraint on W, and the constraint that our familiar constraint of the norm is 1, or W transpose W is 1. This immediately leads to now W is the eigenvector of X transpose X. Let us come back and see what was X here. X is a matrix with all the rows as the samples, but remember the samples were all mean subtracted samples. Now, if you remember, our covariance matrix was 1 by n sigma I is equal to 1 to n xi minus mu into xi minus mu transpose. You will start to see the covariance matrix, or a scaled version of covariance matrix, is what we are looking for. Or the solution to this problem now is the eigenvector corresponding to the largest eigenvalue of, this is a maximization problem, largest eigenvalue of the covariance matrix of this set of points.